So, hello everyone again. This is lecture 7 part 3 of current electricity. This is the final portion of your current electricity portion. In this I will just move on with the every discussion which we held in a brief portion about current electricity. We will start with the introduction and then that will be the end of your current electricity. So, I am Sameer Lavankar. Let us begin our discussion. Okay, so these all were the concepts which we dealt with in our discussion. And finally, in the last portion I explained to you the two different topics of potentiometer. The first was that we need to find out the value of ratios of epsilon 1 by epsilon 2, that is the EMFs equal to L1 upon L2. So, basically what we understood is epsilon 1 by epsilon 2 is equal to L1 upon L2, and next was upon internal resistance, in which we found out the value of internal resistance equal to capital R into L1 by L2 minus 1. Okay. Let us start our summary portion today. So, before summary, let me make you understand that I explained everything. So, in this introduction portion I explained to you what is basically electricity. So, it is nothing but a charges in motion which constitute an electric current. If the charges are at rest, then that does not constitute an electric current. Current electricity is only based on if the electric charges are in movement. Okay. Then electric current we understood a formula called as small I is equal to Q by T, and similarly we also understood that in infinitesimal method it is equal to limit del T tending to 0 del Q upon del T. The SI unit of units is current is amperes, which you should know, denoted by capital A. Then in electric current in conductors we understood the concept of what is conductor. So, basically there are three types of materials, and if the electric field is present, then there will be a conduction or there will be electric current happening. If there is no electric field present, then there will be no electric current passing. There will be no passage of electric current from left side to right side. Okay. Then Ohm's law was being understood. So, basically we understood V is directly proportional to I, or V is equal to IR. Then we understood different concept, how is the value of resistance depending on the value of length and area. So, basically we understood finally that R is directly proportional to L, and similarly R is inversely proportional to A, that is cross sectional area. Using both these equations we understood that R is directly proportional to L upon A, and finally we got that R is equal to rho L by A. What is rho here? Rho is nothing but the resistivity. This resistivity depends on the material of the conductor, but not on its dimensions. Resistivity only depends on material of conductor. So, if the material has been changed from, let us say, copper to nickel, the value of resistivity will change, but if the value of copper is, let us say, A by 2, and we are finding out the value of resistivity at, let us say, area capital A, then the resistivity will not change. Okay. Then a concept called as J, that is current density, which is equal to complete current I by A, that is area was being dealt with, and the current density is denoted by capital A by m square, that is meter square, denoted by capital J here. So, by basically what we found out directly that E is equal to, what is E here? E is nothing but the magnitude of electric field is equal to J into rho. What is J? J is nothing but the current density. What is rho? Rho is resistivity. Okay. Then finally what we got is J is equal to sigma into E. What is sigma? Sigma is conductivity. What is sigma? Sigma is nothing but the ratio, inverse of resistivity. Okay. This thing has been dealt with. Then a new concept called as drift of electrons, or the original resistivity was being explained. So, basically in this these assumptions were being put. So, first of all what we understood that movement of charges constitutes an electric current. Movement in this complete lecture assumption was being put that we are only explaining that the only negative electrical charged particles are in movement, the positively charged particles are not in movement. So, positively charged particles are fixed, as you can see, the negatively charged particles are not fixed. Okay. Then finally what we dealt with that finally what was the value of Vd. So, where it is written. Yes. So, what we got finally was Vd is equal to minus small e capital E by m into tau. What is tau here? Tau is nothing but the relaxation time, that is the average time the electron or the negatively charged particles takes for the collision to happen. Also using this finally what we got is for the original resistivity, that J is equal to Ne square by m tau E. Similarly, by using the formula before we also understood that J was nothing but equal to sigma into E. So, using this as equation 1 and this as equation 2, what we got that sigma is nothing but equal to Ne square by m into tau, and that was the origin of resistivity. Okay. So, this thing was also been explained. Then so these were the examples I explained you clearly in the previous discussions. Finally, there is a concept called as mobility. So, mobility is nothing but just a simple mathematical term. It is nothing but mod of Vd upon capital E. What is Vd here? Vd is nothing but a drift velocity. What is capital E here? Capital E here is the magnitude of the electric field. Okay. Then limitations of Ohm's law. So basically there were 3 limitations in which you understood a concept where sometimes the V is not proportional to I. One was in diode, in which we tried to change the value of potential difference, then the resistor in quadrant 1 or the graph in quadrant 1 is not similar to the graph in quadrant 3. So this happens in diodes, and this is a very peculiar example, or this is a very peculiar application you will understand in your concepts of chapters of semiconductor devices. So this is very important, how we utilize this amount or this type of things in our semiconductor devices, or this resistivity or this limitations of Ohm's law in semiconductor devices. So example of a semiconductor device is nothing but a diode. So this you will understand in your semiconductor devices chapter. Okay. So next is your gallium arsenide. So in gallium arsenide we understood this concept, that is nothing but for initially it is linear, then it changes its direction. So basically we can find out a current I such that you can find out 2 different voltage values for it. Okay. So this was one of the applications. So there were 3 different limitations of Ohm's law. Then resistivity of various materials, so we understood that as the material changes, the value of resistivity keeps on increasing. So as you can see, for insulators the value is a very higher value, let us say 10 to the power 14, 10 to the power 16 and so on, but for conductors is very less, -8, 10 to the power -8. So as you can see, the order is very different, or the range is very high from conductors to insulators. Okay. The next thing is we understood that there are 2 types of resistors, one are called as wire bound resistors, one are called as carbon resistors. We understood the concept of color coding of carbon resistors, in which the first 2 digits, the first 2 bands are nothing but the first 2 significant digits. The third band is nothing but the multiplier, and plus minus this value is nothing but the last digit. So this is first digit for you, this is second digit for you, this is third digit for you, and this is the fourth digit for you. So this was clearly explained. I guess 3-4 examples were being dealt with in explaining this color coding of resistors. Okay. Next is temporary dependence resistivity. So in this we understood that the value of so first of all we understood this linear significance, that is rho t is equal to rho naught into 1 plus alpha delta t. Then in the next portion we understood that the value below 0 degree is not linear, it is of non-linear sequence. So that thing has been explained here. So as you can see that below 0 degree Celsius, that is 273 Kelvin, the value or the graph is a non-linear for resistivity versus temperature. Then we also understood the value of where it is written. So for value of insulators and semiconductors, rho decreases with temperature, but for conductors rho increases with temperature. So this thing was one of the peculiar implication from this point of discussion, that we need to understand for insulators and semiconductors rho decreases, for conductors rho increases with temperature. Okay. So then these were the examples. The next is electrical energy and power, in which we understood the value of power, which is equal to I into V, also P is equal to I square R, which is equal to V square by R. Then we also understood how it is being generated using the concepts of electrodes. And finally we understood the power loss. So basically why we are using a transformer to decrease the value of voltage. So basically to reduce this power loss or ohmic loss, what we do is the amount of power which is coming from this power factories is deposited to transformer, so that the amount of current leakage is very less, but we cannot use that amount of high voltage in our devices. They are not being generalized, they are not made up to have the capacity to generate that amount of potential difference. So a transformer reduces the voltage, a transformer reduces this voltage, and then it can be finally used, or then can be directly used in our home appliances. Okay, so then next was combination resistor, series and parallel. So in this R equivalent is equal to R1 plus R2 plus dot till Rn for series, and similarly 1 by R equivalent is equal to 1 by R1 plus 1 by R2 dot till 1 by Rn for parallel. Okay, next thing was about cells EMF. So a new concept called as EMF, that is nothing but the potential difference was being explained. So this all things were explained. We found that V is equal to epsilon minus IR. What is R here? R is nothing but the internal resistance value. Okay, so these all things were being explained, then examples were being dealt with. Then we understood cells in series and parallel. So for cells we understood that if we are using the value of cells in series, then epsilon equivalent is equal to epsilon 1 plus epsilon 2, and R equivalent is equal to R1 plus R2. What is R1 and R2 here? R1 and R2 are the internal resistances of the EMFs epsilon 1 and epsilon 2 respectively. Okay. Next thing is about the value in parallel. So, in parallel what we understood is, first of all, 1 by R equivalent is equal to 1 by R1 plus 1 by R2. So, right from this we understood the value of R equivalent, and using that in this portion here we can find out the value of epsilon equivalent as epsilon equivalent upon R equivalent is equal to epsilon 1 by epsilon 2 plus epsilon 2 by R2, and so on. If the value of resistance increases, we can just use the value like this, and similarly like this. Okay. So, this thing is also, this was the thing which I tried to explain to you here. So, this is the same thing here. Okay. Then the Kirchhoff rules. Kirchhoff rules is nothing but we need to find out something, some rules, so that we can explain the amount of current passing through each of these resistors in a complex series of resistors in parallel or in series. Okay. So, first for junction rule. So, this was a peculiar example of a junction rule, and then there was a loop rule. So, basically loop rule is nothing but if a closed circuit is happening, we can just explain, or we can try to derive the value of amount of different currents. So, if there are 3 equations and 3 unknowns, you can find out the value of current passing through each of these loops or any wire. So, one of the example was being dealt with, this was a symmetrical wire, and then also one of the example was being dealt with like this, which was some sort of unsymmetrical or less symmetrical. Then a Wheatstone bridge was being explained, in which finally what we found out that these are the battery arms, these were the galvanometer arm. So, finally what we got is, for the balance condition to occur, R2 by R1 is equal to R4 by R3. So, by varying, let us say we know the value of R2 and R1, we know the value of, we do not know the value of R4, we try to vary the value of R3 here, and we will get a value such that R2 by R1 is equal to R4 by R3, then we can find out the value of R4, that is the unknown resistance. Okay. Then an example was being dealt with for galvanometer, not balanced condition. Then meter bridge we understood complete thing. Finally, what we derived is that R is equal to S, R is unknown, S is known, which is into L1 upon 100 minus L1. In potentiometer concept, there were 2 different things. First was epsilon 1 by epsilon 2 is equal to L1 by L2, this portion here for you. Next was nothing but the value that small r, that is to find out the value of internal resistance, small r is equal to capital R into L1 upon L2 minus 1. Okay. So, let us move on with summary now. So, let us move on with the summary now. So, in summary portion here, so let us go on. So, finally, so this is the complete formula sheet for you. So, I guess I have added every formula which was important for this current electricity. You can just add that R equivalent things, I guess these were directly being understood, and you can find out the epsilon equivalent things. The rest all I have already added. So, these are the basic portions. I guess those are not being added. So, basically you may know, right, that R1 by R2 is equal to R3 by R4. So, that can be dealt directly only. Every of the 3 concepts, that is potentiometer, meter bridge and Wheatstone bridge of a balanced condition, everything can be utilized by this portion only. Okay. Rest everything I have added, VD I have added, F sigma I have added, mu I have added, and so on, power also I have added. Okay. So, let us start this thing, and then that will be the end. Okay. So, current through a given area of conductor is the net charge passing per unit time through the area, quite evident, this is the formula given here. To maintain a steady current, we must have a closed circuit in which an external agency moves electric charge from a lower to higher potential energy. The work done per unit charge by the source in taking the charge from lower to high potential energy is called the electromotive force, the basic definition of electromotive force, which I already explained in the previous discussion when we are talking about EMF. Note that the EMF is not a force, this also has been explained, it is the potential difference between the 2 terminals of a source in open circuit. Next is Ohm's law, Ohm's nothing but V is equal to IR. Next is the resistance R of a conductor depends on length and cross sectional area, that is R directly proportional to L upon A, therefore R is equal to rho L by A. Next, electrical conductivity ranges from 10 to the power minus 8 to 10 to the power minus 8 for conductors, and similarly for insulators is 10 to the power 22, 10 to the power 24. Okay. Next is, in most sequences the carriers of currents are electrons, as we explained that was the basic assumption of our current electricity portion. In some cases the ionic crystals and electrolytic liquids, positives and negative ions carry the electric current. So, electrolytic solution was being explained. So, in that portion we understood this complete concepts, that even ion crystals can also be used as that electron charge carriers. Okay. Then current density, so basically we got the value equal to NEVDA, that is the amount for if J is normal to the area, so we can find out the value of VD drift velocity like this. Then anything else, so basically finally found out the value of VD, which is equal to minus E capital E tau by m. What is E here? E is the charge of an electron. What is capital E? Capital E is the electric field, magnitude of electric field. What is tau? Tau is nothing but the relaxation time. What is m? M is the mass. Okay. Finally, using this also we found out the value of resistivity, that is rho is equal to m upon n E square tau. In the temperature range in which resistivity increases linearly with temperature, the temperature coefficient of resistivity alpha is defined as the fractional increase in resistivity per unit increase in temperature. So, what is the formula we used here? Rho T is equal to rho naught into 1 plus alpha delta T. So, this is the alpha being talked about here. Okay. Next is, this is the limitations of Ohm's law being talked about here. Then this is the series resistor series parallel, then Kirchhoff's law. So, this is the junction rule, this is the loop rule, then Wheatstone bridge, for which the balance condition is R1 by R2 is equal to R3 by R4, and then potentiometer applications are being used, that is it can be used for epsilon 1 by epsilon 2 is equal to L1 by L2, and similarly we can use the value of small r is equal to capital R into L1 by L2 minus 1. Okay. So, these are the all different types of physical quantities which I explained you in this current electricity. So, first was electric current denoted by symbol capital I, charge is capital Q or small q, voltage is nothing but capital V, electromotive force is epsilon, resistance is capital R, resistivity is rho, electrical conductivity which is equal to 1 by rho is sigma, electric field is capital E, drift speed is Vd. Please remember Vd is equal to minus E capital E tau by m, this is the value formula, it is a negative sign is also there. Relaxation time is tau, that is the amount, average amount of time an electron or a charge takes for its collision with the different electron. Okay. This is next current density, that is denoted by A by m square, that is nothing but J is equal to current, that is in amperes, or let us say I write current only, current upon area. Okay. And next is mobility. What is mobility? Mobility is nothing but mod of Vd upon capital E. Okay. So, that is the end of your complete summary of current electricity also. So, this is the course progress, we understood everything: introduction, electric current in conductors, Ohm's law, drift of electrons and origin of resistivity, limitations of Ohm's law, resistivity of various materials, temperature dependence of resistivity, electrical energy and power, combination of resistor series and parallel, cells, EMF and internal resistance, cells in series and parallel, Kirchhoff's rules, Wheatstone bridge, and finally in the previous discussion also I explained to you Wheatstone bridge and meter bridge and potentiometer. So, that is the end of your complete current electricity. Thank you for your time, thank you for your patience. Let me stop it here. Thank you so much.